Push that rock with Simpson math. Success starts here at Temple College. In this video, we are going to show a use or application for anti-differentiation, aka the indefinite integration. And we're also going to get a sneak peek at a whole course that's in the calculus sequence called differential equations. So the courses in the calculus sequence are called Cal 1, Cal 2, Cal 3, and then differential equations. Cal 1 is just differentiation mostly. Cal 2 is mostly integration with some look at series. Cal 3 is looking at things in 3 dimensions, functions that have 2 inputs and the 1 output. And then we have this thing called differential equations, and you're going to get a sneak peek at it in this lesson. Okay, but we're going to start with the definition. So the definition is exponential growth and decay describes a change in quantity proportional to current amount. Proportional, that's something you learn in science. So if two things are proportional, you get this relationship. If W is proportional to or volume is proportional to temperature, I don't know that it is, but say it was, then you'd get something like that. Okay, so this change in quantity proportional to current amount. So let's try to apply what we know about this proportional and change in a quantity. So let's say Y is our quantity. Then the change in the quantity is dy dt if we're using t as a time input variable. And then it should be proportional to the amount, which is y. So this definition says that the derivative of the function describing the growth or the decay is proportional to, so this is called the constant of proportionality. Constant of proportionality. I don't know how to spell proportionality. Proportionality. I just wrote it really badly with bad handwriting, so you don't know I don't know how to spell it. Anyway, with the quantity itself. So that's what the definition says. The definition gives us this relationship between the derivative and the function. Okay? Now, here's that relationship. What differential equations is all about is solving equations like this for the function. So that's what we're going to do. Now, the very first step to solving this equation is to algebraically manipulate it. I'm going to multiply by 1 over y. And then I'm going to do that Leibniz trick and treat this as a quantity and multiply both sides by dt, which is weird because on the very next step, I'm going to treat this as just a symbol. And this is just a symbol as part of an operator, not as a quantity. But that was the genius of Leibniz, that he recognized that sometimes you could treat this symbol as a fraction, which I just did when I multiplied both sides by dt. Now what I'm going to do is I'm going to come in and integrate on both sides. So I'm going to integrate here and integrate here. And so now that means that this is my integrand and this is my integrand, and the dy tells me what I'm integrating with respect to. I'm integrating with respect to y. Well, we know what we get on this side. We get the natural log of the absolute value of y and plus some c. Let's call it c1. Over here, we get k t plus some c, let's call it c2. Now, I'm going to drop the absolute value here, assuming that we're talking about positive, on the positive side of the function. So I'm going to drop the absolute value, and I'm going to move this over here. I'm going to subtract a constant from a constant. I get a constant, and I'll call that constant just the constant rather than giving it a subscript. Okay, so far so good. Now I'm trying to solve for y, so that means I'm going to say, oh, logs are equal to the exponent, so this is now an exponent. And the base is e, and it equals y. Oh, that's nice. But I'm going to still do some manipulation. I'm going to say this is e to the kt times e to the c, because if you have like bases, you add the exponents. So if I have a sum exponent, that means there must have been 2 bases multiplied together to get that. So I can rewrite it like this. I think I'm running out of room, so we'll go to another sheet. So what I had was I had y equals e to the kt plus c, but I rewrote that as e to the c times e to the kt, because if they're like bases, I could add the exponents and get back to there. Now all I'm going to do is say, hey, this is, if I put in 0 for time, I get e to the 0, which is 1, and 1 times this is whatever it is, but I get this whenever the time is 0. So we're going to call this the initial amount, and we're going to have y equals some initial amount or quantity. Sometimes we use q here, or y, because y was the amount. So I could use y subscript 0. It just means the initial whatever output is, e to the kt. And now I have the function that describes exponential growth or decay. It would be decay if k was negative. It would be growth if k is positive. And y'all all know this. You studied it in college algebra, that this is an exponential function. Oh, we got it straight from the definition using a little calculus, solving a differential equation. Math made simple. Simpson math.